So, hello everyone. Welcome to Physics 105. So this week we will continue talking about Newton's laws, and we will expand applications of Newton's laws in two topics. First is the friction. We will talk about how to take that into account. And the second one is also very important and very useful topic. Circular motion. How do you describe circular motion? So I think there's not much material today, so I'm hoping to finish early so that we can solve some problems and discuss some of your questions, hopefully, and we'll see. Okay? All right. So this is like chapter 5 in your book, Giancoli. It's on friction, circular motion. I think drag forces are not included, but I think it's a nice read. I recommend, if you have time, you can read that too. So this is like, these sections are your reading, and these are the recommended problems. Hopefully I can solve at least one or two today, and then maybe one or two on our tomorrow session. So let's start with friction. So the friction is like okay, these are the surfaces, right? You can zoom in and say, let me polish these surfaces so that these wedges and heels disappeared. But at some point, you can do this, of course, and decrease the friction to some extent. But at some point, you are going to hit the crystal structure of these materials, and you will not be able to do anything better. So the upshot is friction is microscopic in its origin, and it is actually a very deep topic. It is like a material property, but for this class, we don't actually care about these deep details, right? It's like an engineering problem. You can experiment with different techniques and different materials to reduce it, but at this point, we want to model this with some simple equation and then study its effect. So for this, we start with kinetic friction. This is the friction when two objects move with respect to another and they are in contact. And our simple model is this. So one object has like a normal force. So let's say this object, there's like some normal force. It could be its weight like this. It could be someone could be standing here or pressing on it or whatever. There's like in total, there's like some normal force. And we say that if this object moves in this direction, friction force is in the opposite direction, and its magnitude is proportional to this normal force. And the proportionality constant, mu of k, k for kinetic, is called kinetic friction coefficient. So there are a couple of things to note about this equation. First, you have to be careful that this is not a vector equation. We are modeling the magnitudes of forces. Magnitude of normal force is proportional to magnitude of friction force. So this means you have to determine the direction. And I think it's not hard, at least for this problem. We know if the object moves in this direction, friction force is going to be in the opposite direction. And finally, this mu of k is, like I said, a material constant. It changes from system to system. It changes with like material properties, but generally it's roughly independent of this velocity v, and it's roughly independent of this contact area. So if you look at some experimental results for some materials, I think that's interesting. So for example, okay, wood on wood, you can look at it, it's just like maybe I can think our kinetic friction covering is like 0.2. And you can think about ice on ice. You know it's going to be more slippery, so it's like 10 times smaller than wood on wood. Or metal on metal with some lubrication. You can see it is very slippery, which is like, I think, which is what most machinery relies on. But it is not as good as like ice on ice at this point. Steel on steel, you can see it's not that good. Or this one is also important, rubber on dry concrete. Why? Because our transportation system depends on this, right? You want to have like a good grip on the concrete with your car's tires. And we know when it is wet or rainy, it gets slippery. Here's the kinetic friction coefficient. Or I think there are other examples, Teflon, synovial joints. You know, your joints, they are under constant friction all the time. And I think it's a good thing that this kinetic friction coefficient is small, right, in our limbs. So I think it's interesting to think about these things. I recommend you just look at it, and since you guys are engineers, I think you will have to think about friction in your career in the future. So this is one kind of friction, kinetic friction. There are other kinds of frictions, like there's, for example, static friction. This is when two objects are in contact and there's like a force, but that force is not sufficient enough to move it yet, right? And we model it with this inequality. The friction coefficient in the case of static friction is less than or equal to another constant, we say mu of s times normal force. So we call this the maximum possible friction force. So this friction force increases until you hit this maximum value. And when you hit this, object starts moving and your kinetic static friction is converted to kinetic friction. And a note is mu s is generally bigger than mu k. That's why sometimes moving things initially is harder, but once you start moving, it gets a little easier. Lastly, there's low rolling friction. I mean, if objects roll, there's still a friction, but since that's much smaller than both static and kinetic frictions, we'll completely neglect that in this class. Okay. So that was about friction. Now, circular motion. So circular motion is like one of the most common motion in physics. It's everywhere. Planets do this. If you look around you, everything does this. And I think it has like a nice physics. When we say circular motion, what we mean is motion around a circle, like this, with constant speed. So speed here is v constant, speed here is v constant, but velocity is not constant, right? V is constant, but the direction is changing. So the direction of the velocity is always tangent to circle. So if this is like your circle, and if this is your velocity tangent, they only touch in one point. This is your circle, this is your velocity, they only touch in one point. That's why they are always tangent at every point. Okay? So, and the question is, how do we determine? So, if the direction of the velocity is changing, that means there is an acceleration. And the question is, what is the actual acceleration? So, we need to determine both magnitude and, since acceleration is a vector direction. So for this, we can consider this picture, right? And we can zoom into, like, let's say you are here, in a little bit time later you are here, and let's calculate how much the velocity differed and take the limit so that it's going to give us acceleration. So we can use actually this figure, the zoom in of that same thing. And before that, I want to draw maybe like a, maybe I can do this. So what I want to do is I want to draw exactly this vector and carry it over to here so that I can look at the difference. And from the difference, I can calculate the acceleration. First, let's draw a copy of this vector, okay? And I want to move this guy to here. Okay, now I want to carry this guy, other guy, like this. Okay. Now let's zoom in. So let's look at the geometry here. So I said velocity vector is tangent at every point. So this one is tangent, this one is tangent. But this means that this is 90, this is 90, right? Let's put these angles. So if this is 90. So this guy and this guy are parallel. I just parallel transported this guy to here. So that means this is also 90. So if this angle is delta theta, that means this angle is 90 minus delta theta. Then, since this angle is perpendicular, here this small angle should also be 90 minus 90 theta is theta. Okay, this is delta theta. So what do I need here, right? I want to find delta V, which is V2 minus V1. And from the figure, you can just see what this is. Maybe I can put like a red arrow. V2 minus V1 is this guy. So delta V vector. And now I see two triangles here. One is this triangle. So each side is R and angle is delta theta. And I see this triangle. So now each side is V and the angle is also delta theta. Can I use similarity of these two triangles? Let's look. So I know this segment here, if delta theta is small, I can write it in terms of R and delta theta. Let's do this. Simple geometry. Delta L is equal to R times delta theta. And if I like, I can solve this equation for delta theta. Delta theta is equal to delta L divided by R. Thank you, I messed up. That's exactly, yeah, good catch. Thank you for this. That's absolutely correct. Yeah, V2 minus V1, right? So let's write the similarity for the other triangle. So again, delta V, the magnitude of velocity, should be equal to now side length, which is V, magnitude of velocity is constant at each point in the tangent, times delta theta. Now I think I want to use a different color here. Okay. Now I want to use this theta from here, which means delta V is equal to V times delta L over R. Good. So what was I looking for? I was looking for acceleration. And acceleration by definition is limit of delta V delta t as delta t goes to 0. This is equal to limit delta t goes to 0. What is delta V here? I just calculated this object. And it is V over R delta L. And delta t is delta t. Now I look and I say, okay, this guy is constant, it doesn't change with time. Radius is constant, doesn't change with time. So the only quantity that will change with time is this thing. And I know this limit, right? Maybe I can wait for somebody to write just to make sure. What is this quantity? Limit, as limit goes to delta L over delta t. So change in distance divided by, yes, somebody wrote it, thank you. That's so I took this guy out, and for the rest, this part, I write V, because that's the definition of V. So this is V squared over R, okay? And that's by definition acceleration, which is very interesting. So if, I think maybe I can box this guy. A in circular motion is V squared over R, and its direction is always inward. radial, right? So this vector, as V2 approach to V1, this vector will be more and more and more perpendicular. So at some point it's going to be like this, perfectly radial. So, okay, here is an exercise question from your book, right? The magnitude of acceleration is constant. Then can we use the kinematic equations for constant acceleration we found in the previous chapters for this uniform circular motion? For example, can we use this kind of equation for circular motion? So maybe I can just tell you the answer. We actually can't. And the reason is, yes, the magnitude of A is constant, but the direction is changing. So here, A is pointing this direction, here, A is pointing this direction, here, A is pointing in this direction. Whereas in the projectile motion, if you remember, it was like something like this. At any point, acceleration was in the same direction. So in the projectile motion, it's completely different, okay? You have something like this. So it is different. You have to be careful. So I think this example is not hard. I'll let you do it by yourself as an exercise. But I want to, in passing, I want to define these two things. Frequency is, so you are revolving on a circle, right? And frequency is number of revolutions per second. How many times you complete this circle in 1 second? And the unit of frequency, maybe I can wait. What is the unit of frequency? Yes, 1/2. That's important. Just 1/2. It's not hard, but sometimes people get confused, which is fine. And the period is time required for one full revolution. How much time from here to here do you have to spend to come back? And the velocity, you can write velocity in terms of t, right? Because magnitude of velocity is constant, or speed in terms of t is basically, maybe I can write it just to save time. Total distance, delta x, delta t. We just said it's like full revolution, right? Total distance is 2 pi r divided by total time, t. Or the same thing, 2 pi r times f. Yeah, I mean, you just go through these simple things to make sure you don't sometimes get mixed up. So now I told you there is like an acceleration in uniform circular motion. If there is an acceleration, Newton's law says there is a force. And then we can actually find this force. And this force is, we can look at the radial direction, which is the only direction with the force. And it's just m times a. We just found a to be v squared over r. So then the force in the radial direction or in the central direction is mv squared r. And this is sometimes called centripetal force because it's towards the center. So here, let's clear up some misconceptions. I think some of you may know this, some of you may have this misconception. There is no such thing as center fleeing motion. So when you are in circular motion, you may feel like there is something pulling you out. And you may feel like there is a force. No. For some reason, they teach this in high school and this sticks with people. It takes a while to clear this up. There's no such force, right? If there was force, and I let you go here, your motion would be, because you're like your velocity here, your motion would be like this. Whereas if I let you go here, you'll go in a straight line, perfectly straight line. So there is no center fleeing force in circular motion. There's only force is centripetal force, and it is towards the center. And that's the force that provides that circular motion. Is that inertia? Yes. So basically, yes, exactly. So when the bus stops and you feel like somebody is pulling you forward, that's like actually like a misconception, like a um, like a feeling, right? It's not like an objective reality. What happens is you want to keep moving, but your reference point, the bus stops. So you think that somebody's pulling you forward. The same thing happens here. So in the circle, you want to go in a straight line. That's your inertia, right? You want to go in a straight line, but something pulls you down in. So since you follow the circle, your initial demand to move in a straight line looks to you as if there's like a force this way, but there is actually not. Continue with this example, I think, which is rather nice. And I think this is a fundamental example. You guys may see it later because it's has some useful properties. So this is called a conical pendulum. And in this pendulum, there's like a small ball of mass m, and it just rotates like this. Okay, maybe I can do this. So imagine this red circle is a ball, and it's kind of like the motion you are doing. And here, chord length is given as L, and the angle of the chord is theta. And the question is asking, in what direction is the acceleration of the ball and what causes the acceleration? And we calculate the speed and period time required for one revolution of the ball in terms of L, theta, G, and M. Okay, I will give you a couple of minutes to study this example for yourself. So let's first start with this free body diagram and let's identify the forces. Force is mg. And the only other thing I can see is T, right? T. And this T comes with two components. One is, let's call this Ty. The other one is Tx. So I can already see that this guy should balance this guy. And okay, let's write Ty is T times. So if this is theta, this is also theta, T times cosine theta. So since these two balance each other, I already can solve this for T, which is equal to mg over cosine theta, okay? Now I can look at this radial direction, or like this planar or horizontal direction. And here, Ty, which is T times sine theta, should be equal to m times a, m. And we just found what a is v squared over r. And we know what r is. This is m v squared over, that's actually, the question gives this us, but they didn't have to. We could find from geometry. This is theta, this is l times sine is this r, right? So it is equal to l sine theta. Now the question is, okay, in what direction is the acceleration of the ball? I think we already answered this, right? So these two cancel. The force is in this direction, so acceleration is in this direction, radially. And what causes the acceleration? The cause of the acceleration is tension, right? If you didn't have this tension, it wouldn't have the circular motion, it wouldn't have the acceleration. So in part B, calculate the speed and period. So speed is this guy. We need to solve this equation for speed. And T is here. We already calculated T. So V square is equal to, so let's write mg sine theta over cosine theta. So this is T times sine theta I've written, times L sine theta divided by m. Then V is equal to square root mg L. Okay, m's cancel. So let's clear this up. And I can show you m's cancel. GL sine squared theta over cosine theta. Okay, this is one result. And the second one is asking calculate the period. Okay, so if V is equal to the total path divided by total time, but we already calculated that. 2 pi r is equal to L sine theta divided by t, then t is equal to 2 pi L sine theta divided by V. Let's plug this V in from here. Then t is equal to 2 pi L sine theta divided by G L sine squared theta over cosine theta. I think I can manipulate this to simplify. I think this is like 2 pi in front from this. I think this will be L over G, right? And this will be sine squares cancel cosine theta, I think. But you have to check. So what is interesting is this is independent of mass, right? So this is independent of mass. So any questions? So circular motion, I said you don't have to have circles to have circular motion. For example, if you're in the highway and you're approaching like a sharp curve, you are actually going through a circular motion. And this is actually the case when you are in your car or in a bus and you are taking a sharp turn, you can feel like you are experiencing this mysterious force we just talked about. And how do we describe this, right? We can describe this based on what we just learned. So imagine, like, let's use this one. Imagine you're going in this circle and you're, of course, there must be a force along this direction. And if the road is flat, let's identify the forces. First, there is mg, which is your weight, your car's weight, and there's the normal force. But your tire is in contact with the road, so there's also friction. And in this case, friction is along this direction, which causes your rotation. If this confuses you, imagine imagine what would happen if there is no friction. If there's no friction, you just come here and then just keep going. So nothing pulls you inside, so you cannot complete the circular motion. So maybe if we can just solve this example real quick to see if you understand this. So imagine a 1,000-kilogram car runs a curve on a flat road like this of radius 50 meters and at this speed. So will the car follow the curve or will it skid? Assuming the coefficient of friction is this first and then this, okay? So maybe you can answer this and then I can solve both of them. Is it going to follow the curve or will it skid? You are going through a circular motion and you need a certain acceleration on this direction to be able to complete that circle. And you have to compare this necessary acceleration with what you have. And what you have is the friction, okay? So let's calculate this. What you need is the circular motion centripetal force, which is m, maybe I can use this color, m v squared over r. And all these quantities, m is given, v is given, r is given. And this guy should be less than or equal to, and I don't know if it is so yet, so I'll just put a question mark here, F friction which is equal to mu friction coefficient times normal force, which is mg. So I can just cancel these m's and calculate these two sides. So this guy is v squared over, okay, how do I do this? Okay, this one. Clear 15 times 15 divided by r is 50, 4.5. This is 4.5. This side is mu times g. Mu is, so the other side is what? 0.6. 0.6 times g, 9.8. 5.88. 5.9. So this inequality check, so it will follow the road. So in the second case, I can just put mu s is equal to 0.25. Clear 0.25 times g, 9.8. In the second case, it's like 2.45. Second case, mu s times g is equal to 2.45, which is less than actually v squared over r, so it will skid. So here, okay, here's another engineering problem, right? So if you are the person who is thinking about this problem and you don't want people to get out of the way, what do you do? And that people do is they put banking on the road. You basically put some incline, and when your car approaches, you get like extra assistance from this kind of force because you're on an inclined plane. So this one, I think there is like an example problem about this, so I don't want to waste too much time for this. But when you have something like this, you don't need friction. Why? You have the mg inside and you have the normal force like this, and you can see there is already a component of normal force even without friction, which can provide necessary force for circular motion. Hopefully I will solve a problem about this both with this force and the friction at the end of the class. So let's just move on for now. Are there any questions? So don't we need to know the angle of tires somehow? Because normally in a car, it affects if you can turn or not. Yes, I mean, if you split hairs, there are a lot of things to take care, right? But right now we are just looking at the rough picture and we are saying that your car tires, if you zoom in, they are like this. So they are turning, but they are turning perpendicular to this circular motion, their turning point. So along this motion, we can completely ignore all the details and say this is like static friction. Of course, this is the first approximation, which is pretty good, but you can consider other things. And the first thing you should consider is if the road is flat or banked. And banked roads are generally good for circular motion so that you don't fly out of the way. Okay. So finally, so far I talked about uniform circular motion in which the acceleration was constant or the speed was constant. But in some cases, you can actually have like an acceleration tangential. Right? If you are like trying to speed up something with your hand, initially you have to give it a kick along this direction so it can reach the necessary circular motion speed. So in this case, which we call non-uniform circular motion, the object we assume is still following a circular path. It's like a complete circle, but the speed, this tangential speed is not constant. And to describe this kind of motion, what we do is what we did last week. We just decompose this force and acceleration in radial direction and in tangential direction, and write a Newton's equation for each direction. For example, for tangential direction, the acceleration is basically change in speed, how much this velocity changes or how much the speed changes divided by time. And in the radial direction, at any given point, you have like a v, which is not constant, but still you can use that instantaneous v in this equation to find this acceleration. When you find this guy and this guy, you have the full acceleration. You can just write it in component wise, okay? So first, the force. Let's completely ignore everything else and we are only talking about friction, right? The friction is acting on the car and it's on the car, but who is creating this force? It is coming from the road, right? Friction, the force on the car by the road, and it is in this direction. So Newton's third law says there must be an equal and opposite force for every action, right? For action, we can already tell that it is like in the opposite direction, the same magnitude, and F, and this, whatever is acted on the car should be experiencing the same force. Then it is the road by the car. And I think you can use this example I gave previously. Imagine you put like a piece of paper or like a dust. As the car goes through this circle, you can imagine the dust particles like going through like this, right? What is happening is like this force, this reaction force is acting on these like small dust particles, which are the road basically, and this force just flying this apart. That's why when the car approaches like this, you see dust on this side. Whereas when the car is like speeding up like this, you'll see dust in the back, okay? So let's calculate this problem real quick. A race car starts from rest and accelerates at a uniform rate to a speed 35 meters per second in 11 seconds, moving on a circle track of radius 500 meters. Assuming constant tangential acceleration, find tangential acceleration and find radial acceleration at the instant when speed is this. Okay. So the way I do this is like this. So this guy has two components, right? The tangential acceleration and there is like a radial acceleration. And the tangential acceleration is responsible for taking this car, initially it's like v is equal to 0, and it speeds up, and I don't know, maybe here it's like v is equal to 35 meters per second, right? The full acceleration is happening here to here. Now I can just look at the velocities and time and calculate this tangential acceleration. A is, maybe I can write A tangential to make sure I know what I'm talking about. A tangential is equal to delta V tangential divided by delta T, and change in tangential velocity is from 0 to 35 meter per second divided by 11 seconds. Then the acceleration is, let's calculate, 35 divided by 11, 3.2 meter per second square. Okay. And the second part is, what is the radial acceleration at the instant when speed is this? And when the speed is this, we already know it's like circular motion. So a radial, in the circular motion, acceleration is v squared over r. And that's like what? 15 squared meters squared per second squared divided by radius is 500 meter. This meter. So I have a good unit for acceleration. Let's calculate 15 times 15 divided by 500. 0.45 meter per second square. Okay. So this, vector decomposition is like a very useful tool. You just get used to it. You can decompose vectors in I, J, K in orthogonal coordinates, or you can decompose vectors on a circle in radial and tangential. And it's really making things easy when you can see things like this. Okay, now I think we have a good amount of time to solve some practice problems, which I like. A 4 kilogram block, this guy, is on top of 12 kilogram block, this guy, and which is accelerating along a horizontal table at a 5.2 meter per second square, like this. Let mu k, mu s be equal to mu. What is the minimum coefficient of friction nu between the two blocks to prevent the 4 kilogram block from sliding off? So what friction do you need here so that this guy moves with the same acceleration with this guy? There's no sliding, okay? So is this problem difficult? I want to ask your opinion, or easy. What do you guys think? When you see a problem like this, I think these difficulty levels your book puts may scare you sometimes, right? But I feel like it's not that hard. Table is frictionless, yes. We ignore all the friction on the table. There's nothing here. The only friction we consider is here. Okay. Okay, maybe I can go ahead and start. So suppose we have the friction enough and we ask ourselves, what should the acceleration of this guy be? We have enough friction so that there is no sliding. What is the acceleration of 4 kilogram block? This guy. Okay, 5.2, the same, right? So if there is like 5.2 acceleration, there must be a force. Maybe I can write it like this. Acceleration of, let's call these blocks A, and this one is B, and let's call this table. And just not to make sure we mix things up, we don't mix things up, acceleration of A with respect to table. Actually, this acceleration of B with respect to table is given. This is 5.2 meter per second square. I want to call acceleration of A with respect to table, like you said, should also be 5.2 meter per second, so that no sliding. Okay. So this is, we are trying to solve A. Now I ask myself, so if there is acceleration, there must be a force on this block A. And what is the source of this force? We are assuming this guy is moving with some force, but what is the necessary force here? Friction, right? In this case, friction is like this, and this guy is pulling, this friction is pulling this guy or this direction. So then I can write this. So I can probably set up like some MA times G, and there's some normal force F normal. Okay, and there is this friction force F friction, and here F friction, which is equal to mu times normal force, which is mg. Actually, it is ma times g, ma times g, and this one should be equal to ma times acceleration of a with respect to table, which is 5.2 meter per second square. So these guys cancel, right? Then mu is equal to acceleration of a with respect to table divided by g. We can calculate this. 5.2 divided by 9.8 is equal to 0.53. I think somebody already got it. Yes. This is 0.53. Okay. B, if mu is only half this minimum value, what is the acceleration of block A with respect to the table? Okay. Now B, so if mu is half of this value, it means if mu is half of this value, means 1/2 0.53, which is equal to 0.26, I guess. And in this case, I don't know what A is, but I know the force, right? Let's write it. F friction is equal to mu times ma times g, and this should be equal to ma times a of a with respect to table. Again, I cancel ma's, and a of a with respect to table is equal to mu times g. Mu is, okay, half of this value is equal to this, times 9.8, 2.6. 2.6 meter per second square. This is B. So C with respect to block B. So, okay, C, what is the question is asking? It's asking what is the acceleration of A with respect to B. So acceleration of A with respect to B. That's our convention, right? And that's what? Acceleration of A. So I think I'll use my trick, but you'll be confused, so I will not do it. So acceleration of A with respect to table minus acceleration of B with respect to table, right? B is to the left side, right? B, so no, the force is still acting on this direction, right? Friction is still, so imagine you pull this guy in this direction. In which direction do you think this guy will go? I think friction is like pulling this guy on this direction, so it is also moving in this direction, but it is not going as fast as this guy. They're both going to the right, but this one is going with A is equal to 5.2. This one is going to A with 2.6, half of the acceleration. If you halve the friction coefficient, you halve the force. If you halve the force, you halve the acceleration. That's how I convince myself. Now this guy is asking for like relative acceleration. So A of 8 with respect to table is 2.6 meter per second square minus B with respect to table is 5.2 meter per second square. This is equal to minus 2.6 meter per second square, right? So this minus means to the left. So what is the force that must be applied to 12 kilogram block in A and in B? Okay. This is like a bad problem statement, but I think we understand what they mean and we can set it as. In first case, so F should be equal to M times A, right? And we can isolate the block like this, block B. So let's say this is the force we need to apply, but there is a friction. So here, if the friction on A by B is acting on this direction, friction on B by A is its like action-reaction pair, and it's acting in the opposite direction. Simple. Once you master that language, this is like F friction. Then I can just write, this is F total, right? And F total is F, which is the force I'm looking for, minus friction. F friction should be equal to M times A. Then F is equal to F friction plus M times A. But F friction I already calculated. It's here, right? Let's calculate it again. It's 0.53 times MA is 4 times 9.8 is equal to 20.8. 20.8 Newton plus M times A. Let's clear this guy up. 12 times 5.2, 62.4, 62.4 Newton. I think that's about what? Plus 20.83. So this is in the first case. In the second case, I only need the half this guy because friction is half of its value. So I just do the same thing. And it is like clear 64.662.4 plus 10.4. 10.4 is equal to 72.8. F is 72.8, maybe 73, but I don't care. Okay, that's it. Any problems? So just to remind, just in any problem you are facing, like be ready. Do not look down on the problem. Write every single detail, no matter how mundane these tasks are. Write every single equation like this, so that don't let yourself fall into some pitfalls that's hidden. Sometimes we cannot see, so it's better to just be systematic with any problem. You don't have to be fast. Breathe, take your time, one line by line, write what you need to write. Okay, I'm assuming there are no questions, so let's think about this problem. If a curve with radius 85 meters is properly banked for a car traveling at 65 kilometers per hour, what must be the coefficient of self friction for a car not to skid when traveling at 95 kilometers per hour? It takes time to solve. Okay, it is difficult. What is difficult? Maybe you can. So we aren't supposed to know what does bank mean. Aren't we supposed to know the angle between road and ground since it's banked? Yes. So we need to find this, right? Find the angle first. I don't really get what the question wants. You can find the angle. Oh, I understand. So yes, generally, yeah, the most important difficulty in any problem, in my experience, is understanding problem. Sometimes I don't understand problems. So, and here, I think this problem is a little bit, when the problem is like short like this, you have to be careful. Sometimes it can be misleading. The idea is here, maybe I can explain. An idea 5 meter, so a curve with radius of 85 meters properly banked for a car traveling with this speed. So just to make it simple to explain, let's call this guy V1. Let's call this guy R, and let's call this guy a higher velocity V2. So what the question is telling us is properly banked for a car traveling with this speed. So this means if you are going with this speed, you don't need a friction, okay? You don't need a friction. So maybe I can copy this picture I had here, okay? So what this means is, so when you properly bank, when you properly put this angle in your road, you don't need friction. So this velocity will be good even without friction. So the idea is to find this angle for this velocity completely not taking any friction into account in the first part. And in the second part, adding the friction to see how much higher can you go, okay? Maybe I can start with the first part. Okay, let's do this. I think this free body diagram already has what we need. So we are in an inclined plane. We are familiar with this kind of problem, right? There's like a force gravity acting down. And since plane is a little bit inclined, the normal force is along this direction. And the normal force should have two components, this guy. There's like a vertical component, this one, which should balance mg. Let's write this quickly. So F normal times cosine theta should be equal to mg. Okay, we know this. And the other component, the horizontal component, this guy should be the force for circular motion. So F and sine theta is equal to what? It is circular motion force, mv squared over r. And what is Fn? Fn is, okay, from the first one I can solve Fn. F normal is equal to mg over cosine theta. Then here I put it in the other one. I put this result, Fn here. Then what I find is this equation. Mg sine theta, okay, mg over cosine theta is Fn. Sine theta is this, should be equal to mv squared over r. Maybe I can cancel these m's. Then tangent theta is equal to, what is it? Tangent theta is equal to v squared over gr, okay? Or theta is equal to tangent to the minus 1 v squared over gr. So let's box this guy in, right? You were asking about theta, now I found theta. Okay? So I didn't put the numbers, so I'm not sure about the numbers, but maybe this equation should be correct. Do you guys have any problem with this first part? So here, the important thing is, this is all of these velocities I use is V1. This is V1, this is V1, this is V1, okay? This is also V1. This road is engineered for this kind of velocity. But somebody is speeding up, and this person has to rely on friction. Okay, this is first part. Now the second part, where you have to rely on friction. Now, how do we put the friction? Let's think about this. So friction, we know it's, okay, okay, this one. So this one is mg, this one is this, and we know friction is going to be along this direction, right? Because in the case here, where is it? Here, that was the friction. Now imagine you put the whole thing in an incline, so it's still parallel to the road. So here, let's write this friction force. Maybe I can use the same color with them. This one, a little bit. Okay, this is F friction. Now, what should I do? So what should I do? Let me read the comments a little bit. We need to find components. Exactly, that's what I was waiting for. How can we decide which way car wants to go? I see. So should F sign it? Okay. We need, like you said, we need to decompose this guy. So what did we do? We had like a normal force. We decompose it into. Now we have like a friction force. We decompose its components. mg, we don't need to decompose because it's already one component. So let's do this. So friction has two components. One is, maybe I can still use this same purple color. One is this guy. I don't know, like, okay, like this. And the other is this guy, like this. So this one is F friction. Okay, if this is theta, this is also theta, F friction times cosine theta. And this one, this guy here is F friction times sine theta. Okay, now we can proceed. Let's write these equations, right? First, this vertical direction. So F normal cosine theta should be equal to F friction sine theta, right? Plus mg. This is my equation number one. Maybe I can move it a little bit up to open up some more space. And the second one is along this direction. And that one is what? I have the previous one, Fn sine theta, still there, plus the frictional component, F friction times cosine theta. And this should be equal to what? This should be equal to m v squared over 2 over r. But the important part is this v is v2, the second higher speed. So let's pause and look at these equations for just a second. Shouldn't F sine theta is, okay, I think we talk about this. With the angle, we know the effect of the weight. So we need to find the centripetal force when it is, when we separate each other afterwards. Oh, yes, good. So let's look at these two equations and think about this. What can we do? Okay, we have plenty of time. So I want to just digest these two equations. And I want to look at them and to internalize a little bit more. So let's go back and see the problem. What are we looking for? So we set up our equations. We are sure they are working and we are confident. And let's go back to the question and see what are we looking for? We are looking for the coefficient of static friction. So I didn't put the numbers, but I think you can, I will leave it like an equation. I didn't, I actually did put the numbers, but I don't remember. So I forgot. So let's do this. So what is this guy, right? Friction, we know what it is. F, friction is mu times F normal, okay? So let's put this guy into. So this is mu times F normal, and this guy also mu times F normal, okay? Now, okay, I think I have two equations and two unknowns, right? Like here, what did I do here? I first solve it for F normal, and I put it in the other equation to find theta. Now I know the theta already, so let's solve this for F normal and put this here to solve it for mu. That's what I would do. So for this, what I would do is collect F normal in one side here and solve it for F normal and plug it in here. So F normal parentheses, the first one is cosine theta, and the second one, if I pull this guy to here, I have what? I have minus mu sine theta is equal to mg, then F normal is equal to mg divided by cosine theta minus mu sine theta. Good. Now I can plug this in here and solve it for mu. Let's do this. F normal times sine theta, I'm writing this term here, and it is equal to mg over cosine theta minus mu sine theta times sine theta. Actually, I can do better than this. So let's simplify our life a little bit. So I can also take this inside the parentheses of F normal, right? F normal is equal to mg divided by cosine theta minus mu sine theta. Open the parentheses. The first term, sine theta, plus the second term, mu cosine theta, is equal to m v2 squared over r. Now I have an equation for only mu, right? That's only for mu, and I need to solve it for mu. And I think I can do this. It's a little bit calculation, but not a big deal. So I have mg sine theta plus mu mg cosine theta. Maybe I can cancel these m's. Why would I want to write these over and over again? Okay, let's cancel these guys. M. And maybe I can put this g down there. Okay. Yes, I'll put this g to here. So this is sine theta plus mu cosine theta is equal to v2 squared over gr cosine theta minus mu v2 squared over gr sine theta. Now I collect this mu term here with this mu term, and I put this guy over here. Then this will be like inside mu parenthesis cosine theta plus V2 squared over GR sine theta is equal to V2 squared over GR cosine theta. And I take that last sign here to this side minus sine theta. Then mu is V2 squared over GR cosine theta minus sine theta divided by V2 squared over GR sine theta plus cosine theta. Okay, that's my final result. So maybe if we have time, I can put the numbers. Yes, I think we have time, so I can put the numbers. First, let's calculate angle here. What is the angle? V1 squared, clear this. Okay, now we have to do this like dirty job, you know, we have to dirty our hands with these like things, but I'll do it. So V1 is equal to 65 times 1000 meter per 3500 seconds. This one is equal to clear 65 times 10 divided by 36 is equal to 18.1. 18.05 if you like meter per second. V2 is 95 times 10 divided by 36 is equal to 26.4. 26.4 meter per second. Now let's calculate this theta here. V1 squared, clear 18.05 squared is equal to divided by 9.8 is equal to, and divided by R. Divided by R is 85 is equal to. And I need to take inverse tangent of this guy. Inverse is equal to, okay, this is 21 degrees. This guy is 20. This guy is 21. What is it? 0.4 degrees. Now I will put it. I think that's it for today. I think you should check to see if you can make sense of these numbers. And if you have any questions, you should let me know. For now, today's class is done. I think you are free to go.